Last year, I came across a project similar to this on Instructables and thought it would be a fun project to build and expand on. This uses a 24 GHz mmWave radar sensor that detects the presence and movement of a target and provides information about its distance and position. Reading about what this small sensor could do is what first made me want to experiment with it. I combined it with an M5Stack CoreS3, then developed the software needed to process the radar data, display it locally, and send it to a web-based dashboard. In this video, I'll show you the hardware, how the radar data is decoded, and how the complete system was put together. The radar detects moving targets and reports information such as distance, position, and movement. The CoreS3 processes that data, displays it on its built-in screen, and also makes the information available through a web dashboard on the local network. The project is built around two main components. The first is the M5Stack CoreS3. It contains an ESP32S3 processor, a color touchscreen, Wi-Fi, storage, and the supporting hardware needed to operate as a compact standalone controller. The second component is the 24 GHz mmWave radar module. Unlike a basic motion detector, this sensor can provide position and movement information for detected targets. The hardware connection is fairly simple. The radar module needs power and ground, along with transmit and receive connections for serial communication with the CoreS3. A simple wiring diagram is enough to show the connection, because most of the work in this project was not in the wiring. It was in understanding and processing the data coming from the sensor. The radar does not send ready-to-use values such as target distance or screen coordinates. It sends a structured stream of binary data, which is normally viewed as hexadecimal values. That data contains frame information, target records, position values, movement information, and other status data. Before any of it can be displayed, the software has to identify a complete data frame and decode each field correctly. The available example code did not provide everything I needed, so I developed a custom parser for the raw radar data. The software watches the incoming serial stream, identifies the beginning of a valid frame, checks the expected data structure, and extracts the individual target values. Multi-byte values also have to be assembled in the correct order and interpreted properly before they can be converted into useful position and movement information. Once the data is decoded, the target information is drawn on the CoreS3 display. The radar-style screen provides a quick visual indication of where a target is located relative to the sensor. The display also provides system status and access to basic operating controls. I also added a web dashboard hosted directly by the CoreS3. A computer, tablet, or phone connected to the same network can open the dashboard in a standard web browser. No cloud service or external server is required. The dashboard receives updated target information and displays the radar data, operating status, alarm controls, and adjustable settings. The system also includes an audible alarm and data logging. The alarm can be used to indicate when a target enters a selected area or meets defined conditions. Logging makes it possible to record detections for later review, testing, and software development. Artificial intelligence was useful throughout the development process, but it did not simply generate a finished project from one prompt. I used it to research the sensor protocol, develop portions of the code, interpret test results, and troubleshoot problems. The process still required repeated testing, corrections, and verification using the actual hardware. The main advantage was that it allowed me to explore possible solutions and revise the software much faster. This project brought together several different areas of development: embedded hardware, serial communications, binary data parsing, graphics, networking, and web programming. It is still a hobby and development project rather than a calibrated measurement instrument. Radar performance can vary with target size, movement, orientation, mounting position, and the surrounding environment. But as a development platform, it proved to be a useful way to explore what a small mmWave radar sensor can do. I'll post the project code, wiring information, and additional details on the ARH Tech Lab website. That will make it possible to look more closely at how the parser, display, and web dashboard were implemented. If this video was useful, please like and subscribe. Thanks for watching.